Hello, good morning students. So you must have heard about electric dipole in electrostatic. Do you know what's the meaning of dipole? How does it look like? And what is the electric field due to a dipole in a equatorial point and an axial point? If you have any confusion with that, this video is going to clear that confusion of yours. So students, first of all, you should understand the meaning of a dipole. Dipole means you have two poles together. So in electrostatic, we have a positive pole and we have a negative pole, right? So if I keep a positive pole, or I say a positive charge and a negative charge, a positive charge and negative charge, equal positive and negative charge separated by a small distance. So if I say this is plus q and this is minus q. So this configuration is called as a dipole configuration. And also this should be separated by a very small distance. Okay, I would say this is separated by a very small distance d, or I will say a. A and D both are appearing same here. So yeah, I'll see A. Two charges, equal and opposite charges, separated by a small distance A. Where do we see this in real life? Molecules. Have you heard about dipole molecules? Yeah, we see there. There are some dipole molecules where positive and negative charges are separated by a smaller distance, like H2O, NH3. So here H2O, you must be knowing water, and you must be knowing ammonia, NH3. So you see in those molecules, the center of positive charge and the center of negative charge, they are actually separated by a small distance there. So, and hence in real life, that is a dipole. Now any dipole has a dipole moment, right? Any dipole has a dipole moment, and there is a value of dipole moment given. That is, dipole moment is equal to charge into the distance between them. You must have seen this in different form in your textbook. But you should understand that dipole moment, which is a vector quantity, is nothing but charge into the distance separating these two dipoles. Now, since it's a vector quantity, you should know that it has a direction. You know that any vector has a direction and magnitude. So of course magnitude is q into a, and also it has a direction too. And what would be the direction? Students, you should understand that the direction of dipole is in this way, from negative charge to positive charge. That is the direction of dipole, right? So this is a basic physical quantity dipole that you should be knowing, right? Now let us try to understand the two applications of this dipole, where we are going to find the electric field in 2 points. For a dipole, I am going to find the electric field at 2 points. You already know what electric field is. So for a dipole, there are 2 points where I will find the electric field is. One is at the axial point. One is at the axial point. And second, I'm going to find the electric field of a dipole at equatorial point. Okay, so I'll quickly tell you what is this axial point and equatorial point. So first let's go to the next slide and let's put this into application. The first one, electric field at axial point due to a dipole, right? Electric field at axial point due to a dipole. Now let us see how we are making a dipole. Let us create a dipole, and I will use some other color for this. I'm having a dipole. This is a small dipole I have, right? Now what I'm going to do is I'm going to name this dipole, and in this dipole I'll make this dipole a little more smaller because I need to show the axial point, right? Okay, so yeah, so I will create a dipole in this way. Okay, now you see I have a dipole, and here in this dipole I have plus q and I have minus q here, right? I have plus q and I have minus q, and also the distance I'm going to give as 2d. The distance between the two charges I'm going to give as 2d. Now you might be asking, why am I not giving a? Because there is a certain derivation that I'm going to do. You know what's the derivation? Actually, in that, the distances from a dipole should be taken from the center. Okay, now I'm going to take an axial point, and in that axial point, distance has to be taken from center. So if I have to take the distance from center, then it's like that center point is something very important for me for a dipole. So I would say that the distance between plus q to center is d, minus q to center is d, so the total distance is 2d. That's the reason why I have this particular thing. Okay, so chalo, let us go forward and put my point P here. So I want to find my distance at point P. So this is my axial point. See, my axial point is a point which is actually lying on the axis. If I say it actually lies on my axis from the dipole, you see, it actually lies from the axis from the dipole. Now let me quickly put the distances. Let me say the distance from the center of the dipole to that point is r. Okay, so this is very much important. I will say from the center of the dipole to that point P is r. Right, now you have r, you have d. Okay, now you need to find the electric field at this point. Okay, my target is to find the electric field at this point, and that is what my derivation is about, isn't it? Now, to find the electric field, I need the electric field due to positive charge, electric field due to negative charge, because dipole is a combination of positive and negative charge. So now electric field, I would say I'll take electric field of due to positive charge. You look, electric field due to positive charge is Q divided by, or let's put K. Q, K is a constant. What is the distance between the point P and the positive charge? You see, it is actually R plus D. Okay, it's actually R plus D whole square. It's R plus D whole square. Now same way, the electric field due to the negative charge, E negative, is going to be K into Q R minus D whole square. You see, minus D, R minus D I need to put, R minus D whole square, right? Now if I want to find the net electric field, I just need to add them. I cannot add them simply, I need to do vector addition, because electric field is a vector. You must be knowing electric field is a vector, so I need to do the vector addition of it. So let me do that vector addition. If I technically see how the vectors act, you see, if I consider this point as a point, okay, if I consider this point, I know that my electric field vector due to positive charge is going, electric field vector due to positive charge is going away in this way, E plus is going away in this way, and E minus is going towards this way. E minus is going towards this way. All right, and you also know E minus, I'll put my, rather E minus I'll put, yeah, like this. Now tell me students, if I want to find the total electric field, should I do E plus minus, because since they are in opposite direction, okay, both the vectors E plus and E minus are in opposite direction. So E plus is bigger or E minus is bigger? Think. You will know that E minus is bigger because the point P is near to minus Q. So this is how you are going to do. So your E minus is minus E plus. E minus or minus E plus. Alright, now when you are doing this, you will be getting KQ common outside, right? And you are going to do 1 by R minus D whole square. Then you have minus of 1 plus R plus D whole square. Let's go to the next page, shall we? Because it's completely filled. Okay, so when I do this addition, you see the net electric field is turning out to be in this way. The net electric field is going to be K, Q, then you have R square minus D square, okay? Then you see here what is going to happen. You are going to have R square plus D square minus R square minus D square. So on top, R square plus D square, then you have, the positive part will go forward, 2RD minus R square plus D square minus will become plus 2RD. Okay, so you see on top you have KQ into R square, D square, R square, this is also minus, students, D square gets cancelled. Finally, you have 4RD divided by R square minus D square whole square. R square minus D square whole square. Okay. Now, now I have to take a small assumption. The small assumption is that R is very much greater than D. Okay. Because in the example of a dipole itself, we say that D is very small. So I will assume R, the distance of the point, is very much greater than D. It's going very far. So hence in that case what happens? D can be ignored. If I ignore D, I will be having something like this. K, Q, 4RD divided by R power 4. So R will get cancelled and you have you have K, Q. Now from here K, Q into 2 into 2D divided by R power cube. Okay. Now you see here, Q into 2D, student, is dipole moment, isn't it? Q into 2D is dipole moment. You check here, I told you the dipole moment is charge into the distance between them. Okay. So hence, I have the electric field due to axial point. The electric field due to axial point as K into 2 into dipole moment divided by RQ. Now students, you see here the direction of electric field and the direction of dipole moment are same. Okay, the direction of electric field, the direction of dipole moment are the same. How is that happening? So I will tell you. I told you that the electric field due to the negative charge is stronger, right? Electric field due to negative charge is stronger. So if you see the negative charge, the direction of negative charge is this way, isn't it? The direction of negative charge is in this way. So dipole is also in this direction. So when electric field of negative is bigger and dipole moment is in the same direction, so that is the reason why the electric field's direction is same as the dipole's direction. Now students, we will try to understand the electric field due to a dipole in an equatorial point. Okay, so let us look into it. Electric field due to dipole for dipole in equatorial point. Okay, so first of all, you try to understand what is an equatorial point. Okay, let me make a dipole. Let me create a dipole. Dipole is this, a simple dipole, as you can see, right? And this is the equatorial point. The point from the center of the dipole to the top. The point from the center of the dipole to the top is called as the equatorial point. Now I will give the names accordingly, students. Look here, I call this positive Q, I call this negative Q. All right, I call this positive Q, I call this negative Q. Now you see here what I'm going to have is this distance is D, right? This distance is also D because the total distance between the two charges is D, 2D. Okay. Now, if I want to find the electric field at this point, students, look here, if I want to find the electric field at this point, you see, I need to draw a triangle, isn't it? I'll get a triangle like this, and also I'll get a triangle like this. Okay, I'll get a triangle in this form. Now, something you have to understand here. Okay, so my electric field is in this direction. Okay, my electric field in this direction. So what am I going to do is, let's find the direction of electric field. So in this, you might observe that in this case, electric field due to positive charge is in the opposite way. Correct? It is in the opposite way, E. And the electric E plus, an electric field due to negative is attractive, and it is in this way, E minus, E plus, and I have E minus. Now what I can do here is I can resolve E plus and E minus in two components. Okay, I'm going to resolve in two components. When I resolve in two components, I'm going to show the components. Students, one component is like this for E plus. Now I will resolve E plus. E plus is one component is like this, one component is upward. This component is going to be E plus cos theta. Now I will tell you where is this theta. Okay. For E minus, there is a component here which is E minus sin theta, and this is E minus cos theta. Okay, and for for E plus, the up component is E plus sin theta. So you see my electric fields, one is positive electric field in this direction and one negative electric field in this direction. They both are getting resolved here. They both got resolved, and once they get resolved here, I got two components, E plus cos theta and E minus cos theta, and theta is nothing but this angle which it is making. Okay, I will say theta is this particular angle. Okay, theta is this particular angle. Now E cos theta, E plus cos theta, and E minus cos theta. Now where is the resultant? You see, both these sine components are in opposite direction. You see E is having same magnitude because they are from same charge, and distance is also same. You see R, this is distance R, this is distance R. They both are side of a similar triangle. They both are side of a, you see, they both are the side of right-handed triangle. So this R and this R is actually same. Distance is same, charge is same. So electric field value is also same, isn't it? So my E plus is actually equal to E minus. My E plus is actually equal to E minus here. All right. Now, so E plus sine theta and E minus sine theta will be same in magnitude. Understood? It will be same in magnitude. and they are in opposite direction, they will get cancelled out. Sine component will get cancelled out. But here cos component are in same direction and will get added up. Cos component is going to get added up, students. Okay, so when I add up cos component, it is basically going to become E cos theta. All right, so it's going to be my net electric field. My net electric field is going to be 2E cos theta. The magnitude is going to be 2E cos theta. Direction you saw, but the magnitude is going to be 2E cos theta. Right? Now, let me substitute my E value. What's my E value? Electric field. You can see that my electric field value is going to be K, Q. What's the distance between them? You see the distance R. R is going to be equal to, sorry, not this one. I will say this distance, the distance from the center, I will take it as R. I will change the name of R, okay? Because in your textbook, the value of R is different. So let me take this as some random value Z. So again, they both are same. Z and Z both are same. So electric field value is same only. So this is R. I will take this as R. Okay. The distance between the R should be the distance from the center of the dipole to the point of the to the point where you have to take the electric field. So it's going to be basically Z square. So where I know that Z square is equal to K Q divided by Z square is equal to R square plus D square, Pythagoras theorem. Okay, R square plus D square, we have the Pythagoras theorem. So now I'm going to substitute that value, but before that I need cos theta also. I need cos theta also, right? So my cos theta here in this case is going to be, look at this triangle, cos theta is going to be D divided by root of R square plus D square. All right, root of R square plus D square. So my cos theta is also ready, my E value is also ready. Okay, my E due to positive and negative is ready. Now I'm just going to substitute that positive and negative E here and find the total electric field. So my total electric field, students, here is going to be 2K into Q by R square plus D square into D divided by root of R square plus D square. See now, students, you have E is equal to now K into Q into 2D divided by R square plus D square power 3 by 2, power 3 by 2 now. Okay, because we are multiplying R plus D into root of R plus D, so power 3 by 2 it becomes. Right, now you very well know that Q into 2D is dipole moment. So my electric field is equal to, at that point, is K into dipole moment by R square plus D square 3 by T. Now I can bring my assumption again here. If I bring my assumption that R is very much greater than D, if I bring my assumption R is very much greater than D, it is going to become, my new equation is going to become, to equatorial point, my electric field due to equatorial point is K P divided by R power 3. Okay, because if D becomes 0, so R square into power R square power R3 by T is going to give me R cube, right? So I get my R cube, electric field at equatorial point. Now students, you can also simultaneously see the electric field at axial point. The electric field at axial point is K 2P by R power 3. So what does it say? It says that for a dipole, the electric field at axial point is two times, can you see, twice as electric field at equatorial point for a given distance. Remember, distance has to be same, r has to be same. If r changes, then this value will not be equal. Okay, so for a given distance for a dipole, E axial, okay, E axial is going to be twice E equatorial. E axial is going to be twice as E equatorial. Right? So students, I hope you have understood the how to work with dipole. This is a very important topic when it comes to dipole. So I feel that this particular video has made your journey to understand dipole moment more easy for you. So we will come with more videos like this in the future. So students, please do like, share and subscribe this video. It will be very helpful if you subscribe this video, because I want to share the knowledge with you and you have to be there to receive the knowledge. So if you subscribe this video or subscribe this channel, I will be very happy, and you also will not miss out from any knowledge that I'm going to share with you. So students, with this I will end this class and this video today, and we will soon be, I'll come out with another video. So until then, adios. Hello students, I hope you found this useful. This video was interesting for you. Now students, as a part of my journey to make physics easy for you, I have started an initiative, and that is I'm going to help the students who are in their IBDP level, who are going to take their ASA level examination, and those who are in CBSE going to take the CBSE examination. I'm going to provide one-to-one training for you. And in this one-to-one training, I mean that it's going to be a personal attention. I will be taking class for you personally, and also I'm going to make a roadmap for you until your examination. So I'm ready to help for you in physics and to be successful in the particular examination that you are going to take. But students, let me tell you, my time is limited. So I might not be able to take everyone who's registering. So it's better first come, first serve. And students, I hope this thing will be useful for you. And if you want to register, please click in the link below, and do not forget to like, share and subscribe to Physics Revolution. So until then, adios.